Good afternoon, one and all. Present in this session, session number 3 for design. And in today's session, lecture number 3, we'll discuss about the basic design procedure for shaft, gears, then design of rolling and sliding contact. For all these are the machine components wherein shaft or shafts are the basic power transmitting mechanical element which receives the power from the source generating it and transmitting the power, the machine consuming it. Now, when we say consuming it, it means the power which is developed and generated at one place is transmitted over some distance to some new setup at another place using this element known as shaft. Now, when we say shaft, we can say that shaft works as a postman. It receives something and it delivers to some another. Now, while doing so, the faithfulness of that delivery, the faithfulness of that torque transmission is of utmost importance. Because the torque or the power which is being transmitted through this shaft itself will have some impact on the strength of shaft. Now, when I say strength of shafts, basically we must first understand what is shaft. It is generally a circular rotating mechanical element. It is generally a circular rotating mechanical element which transmits power from the source generating it to the machine consuming it for doing some useful work. Now, how many sources of power are there? Number 1, IC engine. Number 2, turbine. Number 3, electrical motor. Nowadays, it is solar energy also. But still, we'll confine our discussion to the very basic sources of power. Now, how many machines will consume it? Let it be automobile. Let it be the machine tools. Let it be any other equipments, ancillaries, which works on the basic principle of rotation of shaft. And henceforth, we say how shaft works on the basic principle of receiving the torque and transmitting the torque, so it acts as a postman. Now, how we can classify shafts? Well, depending upon the applications, shafts are classified as a transmission shaft. The best example is propeller shaft in automobile, wherein it is transmitting some power. Machine shaft, it is the integral shaft. Integral shaft, that is nothing but spindle of machine tools. That is the integral part of the system of the machine. And third one is axle. Now, generally axle are of two types, live axle and dead axle. We're talking about if live, definitely it will rotate. But if it is dead axle, in that case, its shape may not be circular, but it will help to transmit torque or power or circular motion through its existence or through its fabric. It means that it helps in transmitting power, although it is not itself transmitting power. And the best example is in commercial vehicle, heavy commercial vehicle, the front axle. Generally, I-beam section is there. It is not rotating, but through kingpin and the arrangement, the axle is allowing the wheels to rotate. That's why it is a dead axle. The next one, so this is all about definition of shaft and classification of shaft. Now, shaft is the basic mechanical element in any machine or mechanism where rotation is involved. Let it be gear, let it be bearing, let it be flywheel, let it be belt drive, let it be chain drive. whatsoever type of power transmission from one place to another, shaft will be there. Now, while transmitting power, the material of the shaft is again a very important factor in deciding its strength. Yes, in deciding its strength. And henceforth, selection of material is again a very important aspect. Generally, ferrous, non-ferrous material, again non-metals are also there used as a shaft material. Generally, shaft uses alloy steels, generally hot rolled plain carbon steel, cold drawn plain carbon or alloy composition. These are the generalized materials used for the manufacturing of shafts to be used in transmission of power. Now, design considerations. How shafts are designed. Basically, the design of shaft is governed by the torsional equation, that is T by J is equals to tau by R is equals to G theta by L. This is known as a simple torsional equation. Now, what does this torsion equation tells us about? See, this is the equation T by J is equals to G theta by L is equals to tau by R. So what does it tells us? It tells us about on what factors and what should be the factors considered while designing a shaft. While designing a shaft, there are two factors. Number one, the torsional strength, twisting, torsional strength. Number two, its stiffness. Now, again, stiffness is defined or categorized under two sections, that is torsional stiffness and lateral stiffness. Because when I say shaft, what is shaft? So shaft is a circular power transmitting element. Obviously, it will receive power from some source. So while receiving from some source, it means it will have some mountings over it. Definitely, it may receive power from the source in the form of belt drive, in the form of gear drive, in the form of chain drive. In that case, the power source will have a belt drive and a pulley on its outer shaft, and the shaft under consideration will have a pulley. So again, this mounting will be there on the shaft. It will have some load, it will have some thrust, some belt tension, some chain reactions. Obviously, if there are gears, and definitely it will transmit it to some another machine for doing some useful work, for imparting some desired shape on the workpiece in machine tools. In that case, again, it will transfer with the help of some medium, some mounting. Now, for shaft to be held on the position, we use bearing mountings. So bearing mountings will be there. So there may be the chances where shaft may get bent. So again, that stiffness, we consider that factor. So the next element is, now see, when I say designing of shaft based on strength, design of shaft based on strength, so how the shafts are subjected. This is a very basic question, how shafts are subjected. Now, when we say shaft or the design of shaft, it means that the shaft will be subjected to pure torsion or twisting. The shaft will be subjected to bending. Shafts will be subjected to combined twisting and bending moment. And number 4, the shaft will be subjected to twisting and bending along with the axial thrust, as in the case of propeller shaft of the ship, wherein twisting will be there due to the movement of the propeller, the blade. So this will generate a torsion or a torque. Obviously, for the sake of understanding, we may say that the shaft may bend. Now, I can draw a simple diagram where we can correlate this figure. Now, see the diagram. Now, in this case, this is the propeller of the ship. This is the propeller of the ship. Now, the bearings are mounted inside the ship casing, but this propeller will be out of the ship casing and will have a impeller. Now, the twisting moment will be there on the impeller due to the motion of the shaft, as well as this shaft. This shaft may bend in this fashion, Yes, so twisting as well as bending. And the third thing, which is again very important, is nothing but, please mind well, the axial thrust on this blade, by virtue of pressure of water, which will try to thrust or shift this blade and thereby shaft from these bearings and in this direction. So this is the case, fourth case, that is shaft subjected to axial load along with twisting and bending. The basic torsional equation is written here as P by J is equal to G theta by L is equal to some tau by R. So what is tau by R? That tau by R is nothing but the shear stress upon radius. Now we'll continue with shaft subjected to twisting only. Now when the shafts are subjected to twisting, maximum shear stress developed in a shaft subjected to torque is given by tau by R is equal to T by J. What is this tau? It is the maximum induced shear stress in the shaft material by virtue of this torque with this polar moment of inertia of this shaft section in rotation, obviously. So P is twisting moment or torque acting upon the shaft, J polar moment of inertia of the shaft about axis of rotation. Now, if the shaft is solid, when I say if the shaft is solid, in that case the diameter of the shaft, say this is the diameter of shaft, so in this case it is D. If I say hollow, so it will be like this. So hollow, a hollow circular shaft. So outside diameter would be DO and inside diameter would be DI. So this is the diagram. Wherein I can say that the solid shaft and the hollow shaft. But since we know that P by J is equal to tau by R, this J is known as polar moment of inertia. Now its value for hollow and solid shaft will change accordingly, and henceforth these are the two different equations wherein we can say that pi by 32 d raised to the power 4 and pi by 32 do raised to 4 minus di raised to 4. So the dimensions of the shaft subjected to torque can be determined from the above relation. Next element, design of shafts subjected to bending moment. Now let us say this is the shaft having some flywheel, having some gear drive, having some flat belt, V belt, roller chain. In that case the shaft may bend. Laterally. With this equation, I can say that M by I is equal to sigma B by Y. With this equation, I can very well calculate the bending strength of the shaft, which should be less than the tensile or the bending strength of the material allowable. So again, this is for solid shaft and this is for hollow shaft. Where what is y? Y is the distance from the neutral axis of the outermost fiber, d by 2 or do by 2. Please mind it well. For solid shaft, it is d by 2. For a hollow shaft, it is do by 2. Because outermost fiber, distance of outermost fiber from the neutral axis will be. So this is how the equation of shaft subjected to bending will be derived and will be used. Here, I is moment of inertia. In the previous equation, it was polar moment of inertia. So this is moment of inertia of the cross section of the shaft. Next, now shaft subjected to combined twisting and bending. When we say tau T by J is equals to tau by R, sigma B by Y is equals to M by I. Substituting the value of diameter, the equation in terms of stress and torque will be, and bending stress and bending moment will be in this fashion. Next, since these are the two different elements, we'll use maximum shear stress theory and maximum principal stress theory. The maximum shear stress theory is valid for a ductile material, as we have seen in the first lecture itself. So we will use that theory and we'll find out the maximum shear stress. We'll find out the maximum shear stress in the material of the shaft using the equation, wherein we will use both shear and bending strength, and we'll calculate equivalent twisting moment. So PE is the equivalent twisting moment or torque, equivalent twisting moment, and this ME is equivalent bending moment. So please mind well, based on these two equations, we can solve number of problems on this equation. Where what is sigma B? Bending stress, design or working bending stress. Tau, design or working bending twisting or shear stress. So these are the equations in terms of M and T reduced to the final equations. I hope you are getting the basic element, that is the shaft. Design of shaft is based on two criteria: design of shaft based on torsional strength and design of shaft based on stiffness. So this is how the shafts are designed, based on both the twisting moment and bending moment. Previously it was based on bending, and then it was based on twisting alone, bending alone, combined twisting and bending. The next, shaft subjected to axial load. Excuse me. Shaft subjected to axial load means axial load alone. But as we have discussed, as we have seen this example, wherein we can say that this is the propeller of the ship, a large ship, Titanic. Just take the example of Titanic. So this is the large propeller of the ship. Now in this case, all the three, that is twisting moment, then bending moment and axial thrust, all three will act simultaneously, and hence we will use ASME code for the design of shaft. Why? Because now combined twisting and bending will be there, as well as axial thrust will always be involved. Then we'll have to look after the ASME code for the safe design of shaft. Now, when we consider ASME code for the design of shaft, we must consider these two factors, KB and KT, known as fatigue stress concentration factors in twisting and bending. If it is twisting, KT. If it is bending, KB. So that the design of shaft will be safe. And henceforth I can say that when the design of shaft is safe, we must understand this fact. For the safety of the shaft, we have to consider these factors. Now, value of KB and KT for different types of loading. Shaft will be subjected to different types of loading such as gradually applied load. When I say gradually applied load, it means at the initial position of the shaft, at the initiation of the motion or rotation of the shaft, the load applied will be gradual. Sometimes suddenly applied load with minor shock may happen in case of gears, may happen in case of belt slip. So a minor shock is expected and suddenly applied load that depends on overloading of the shaft. When I say overloading of the shaft, it means that is very important. Please concentrate on these figures and these numbers. So you will have an idea as to how the things will change. So in this case, for gradually applied load, the value of KB is 1.5 and KT is 1. For suddenly applied load with minor shock, 1.5 to 2 and 1.0 to 1.5. Now for suddenly applied load, obviously heavy, medium or heavy shock, KB will be 2 to 3 and KT will be from 2 to 3. Okay. Now design of shaft based on rigidity. When we say, so this is all about design of shaft based on torsional strength. When I say based on rigidity, so in rigidity, we have got two different criteria, that is torsional rigidity and lateral rigidity. What we have discussed right now is the lateral rigidity, wherein number of mountings are there on the shaft. This is the bearing, and the shaft may bend in this direction if it is simply supported. If it is overhang, it may bend like this. So overhang, both side overhang, cantilever, etc. So that is lateral rigidity, but we don't want it to bend, and henceforth we say that it is lateral rigidity that should be provided on the shaft. The next one is torsional rigidity. We don't want our shaft to get permanently twisted. So we do expect and we have to consider the rigidity of this shaft, torsional rigidity of the shaft. Now, this torsional rigidity, say torsional rigidity. This is the equation. E by J is equals to G theta by L, or simply theta, that is torsional rigidity, that is angle of twist depends on TL by G into J, where T is torque applied, L is length of shaft, J is polar moment of inertia of the shaft, and G modulus of rigidity. So G is basically material property. Every material has got its specific value of modulus of rigidity. Therefore, for the known values of T, L, and G, an allowable value of angle of twist, the diameter of shaft can be calculated. Because J, pi by 32 d raised to the power 4 is the polar moment of inertia for solid shaft. If it is hollow, pi by 32 d raised to 4 minus di raised to 4. So torsional rigidity is again a very important consideration in the design of shaft. Why so? Because it helps the shaft to retain its original shape and position. See, torsional strength means the shaft may fall in this way, two pieces apart. But rigidity is to provide the permanent deformation. Mind well, torsional rigidity is to resist permanent deformation. Let the deformation is slight, but under twisting, so it may twist and may retain like this. So in this case, if it gets twisted and if it is a torsional rigidity is less, in that case the shaft may get twisted permanently, and the distance between gear to gear or the belt drive or the chain drive will get disturbed, and we don't want to get these distances disturbed, as these distances should be maintained, because PCD to PCD will come on to this particular point in the design of gears itself, wherein PCD to PCD of driver should be in contact with the PCD of the driven, and a tangent should be passed between them. A common tangent will pass then and then proper transmission of gear or the motion will be possible. Otherwise, there may be a number of problems we will discuss later. So this is the first equation, torsional rigidity of shaft. Now the next one is a lateral rigidity. The simple equation of deflection. M by I is equals to E into d2y by dx square. So this d2y by dx square is used to find out the boundary condition for the value of deflection y, based on x, that is distance x. So this is the equation for lateral rigidity. And hence, my dear friend, lateral rigidity is very, very important. Again, it will change the distance, and the shaft, if it gets permanently bent, then whirling may occur, bearing may get damaged. Mind well, what I am discussing now is shaft. If the shaft gets permanent deflection, a slight deflection, obviously at higher speed, the danger of shaft breaking or whirling will increase, will enhance the condition of that particular, or severity of that condition, the severity of that damage will be there if it is bent. We don't want our shaft to get bent. That's why this property or this element should be laterally rigid, so that there should not be any permanent bending. Next one, these are some of the question and answer which were asked in the previous papers. So I have discussed some of the example where possible. So according to MSC code, ASME code, maximum allowable shear stress is taken as X% of yield strength or Y% of ultimate strength. Those I have gone through design data book by Professor B.D. Shivalkar. They'll get this in the data book itself. So the answer is 30% of yield and 18% of ultimate. So the answer is A. If allowable shear stress in the shaft is 70 megapascal and the torsional and bending moments are 1100 number and M, maximum bending moment, find the diameter of the shaft. So here equivalent bending moment or equivalent twisting moment can be very well calculated using the equation which we have discussed. And with this, we can calculate the diameter of shaft. If yield strength is 400, find the permissible shear stress according to ASME code. So ASME standard ASME equation was there. We have to consider accordingly, given the hint also, so that one can very well understand what would be the answer. Okay, so flexible shafts have in torsion making them flexible. So the answer is flexible shafts have high rigidity in torsion making them flexible. You might have heard the basic concept of flexibility of shafts in the dynamics of machines, wherein we have discussed flexible shafts in use. So, calling it back, design of shaft. So based on design of shaft, we have class body shaft, transmission shaft, machine shaft, and axle. These are the basic classification. Then material, then how shafts are designed. Shafts are designed on the basis of strength and on the basis of stiffness. We have gone through the different equations and the different conditions of design of shaft. Based on these conditions and this equation, we can solve number of problems on these equations. So these are the few to solve it, and if you find any difficulty, you may please contact. Now, the very next topic after the design of shaft is gears. Now, shaft is the fundamental and the basic power transmitting element. Shaft is supported by bearing. Now, when I say shaft is supported by the bearing, now this shaft needs some other mountings to transmit power from one place to another. One way is line shaft, wherein shafts are connected in the form of line shaft as the couplings. Now, with this coupling, we can see that the power can be transmitted along a linear direction. Factory shaft. The example is factory shaft, overhead shafts. Then in many cases the shaft is transmitting power to some another shaft with the orientation of axis as parallel, perpendicular, inclined. So in these cases, we may use different types of gear gates. Yes, for parallel shaft, the power transmission between the parallel shafts, we may use spur gear and helical gear. We may use spur gear and helical gear. We may use spur gear and helical gear. Okay. Now, when it comes to transmission of power between an inclined shaft, then in that case we may use bevel gears, or at 90-degree also bevel gears. And the last but not the least, with higher velocity ratio, we may use worm and worm gear. So, for transmission of power, gears are the much trusted mechanical element because it is having positive torque transmission, as there are a number of teeth which meshes with each other, and hence no slip occurs, as in the case of belt drive. As in the case of belt drives, let that belt drive be flat belt drive or V belt drives. The slip may occur during the power transmission, and henceforth we can say that the gear drives are the positive drives. Now, what is gear? Or what do you mean by gears? Gears are the toothed members which transmits power or motion between two shafts by meshing without any slip. Hence, gear drives are also called positive drives. In any pair of gears, the smaller one is called pinion. The smaller gear is generally known as pinion in a pair, and the larger one is called gear, immaterial of which is driving each other. Sometimes pinion may drive gear, sometimes gear may drive pinion. Doesn't matter. When pinion is the driver, it results in step down drive. What do you mean by step down drive? Now that is very important. Step down and step up. So here I'm hatching. The shaft which I'm hatching is a driver. Okay. So this is driver. So here, smaller one. Now see, this is the right. Wherein we can say that, say number one is smaller. So this is pinion. Number one is smaller. So this is pinion. Okay, this is pinion, and this is gear. Okay, so when pinion is the driver, it results in step down. Say for example, the ratio of these number of teeth or the piece circle diameter, or simply the diameter is, say this is some 50 mm, then this larger one is 200. The ratio is of 4. So when this is rotating with 100 rpm, it will rotate with 25 rpm. Yes, because when it will complete one rotation, the smaller one will complete one rotation, the larger one will complete 1/4 of the rotation of the larger smaller wheel, and henceforth it is called step down drive. This number one is step down, and when a larger gear is driving a smaller pinion, then what it would be known as? It would be known as step up drive, step up drive, step up drive. Yes, sir. So this is the basic meaning of step down and step up, wherein when a small gear, that is pinion, is the driver, then it is step down, and when the larger gear is the driver and the driven is smaller, it is called step up. Okay, so this is how gears will be. Now there are different types of gears. Now we must concentrate on this slide, as it is very important to understand the basics of gear, its location, and how it will transmit power between the different orientations of shaft. Now let us say number one, spur gear. Now in the diagram itself, we can very well see that in say spur gear, when I say spur gear, in this case, we say that the tooths are parallel to the axis of the gear. The orientation of the tooth are parallel to the axis of the gear. The next one is helical gear. Now when I say helical, the tooths are inclined. To the axis of the gear. Next, number C is again the repetition, that is double helical gear, and generally known as herringbone gears. The next one, internal gear, sometimes sun and planetary gear. Okay, this system is used in differential assembly of the automobiles. The next one is rack and pinion. F, again very important, bevel gear. These bevel gears are used to transmit power between inclined to perpendicular shafts. The next one is hypoid. Sorry, number G is spiral bevel gear. Spiral bevel gear. The next one is hypoid. Now when we say hypoid, it means the orientation of the tooth is curved. Next is worm and worm gear, and then spiral gear. So worm and worm gear, we will see it in detail about worm and worm gear, wherein a gear is run through or run by number of threads in quantity, say 1, 2, or 3. So we'll discuss it later on, but this is the very important slide, wherein all the different types of gear pairs are there in this, along with their orientation. Now the geometry or the nomenclature of a general spur gear. Now see, when going through your papers, the most important element which I have found out in spur gears or in the gears is the nomenclature. You have to work on this, and that's why I have specifically, and I'm specifically concentrating right now on the nomenclature of this. Now, gear profiles, either cycloidal profiles or involute profiles. Right? We must understand and we must know the difference between the involute, what do you mean by involute profile, and how it is there. And number two is involute profile and cycloidal profile. It is not there in the PPT. Cycloidal profile, that has to be explained during the lecture itself. So involute. So when I say involute, we have seen this type of curve. in engineering graphics. Engineering graphics. So this is involute. This is involute. This is involute. Involute profile. When I say cycloid, cycloid is the curve generated by a moving wheel on the straight surface. So this is cycloidal profile. So this below one is the cycloidal profile. This is the cycloidal profile. So involute and cycloidal profile. So the tooths are cut either according to cycloidal profile or according to involute profile. Generally, involute profiles are preferred. Why easy to cut and the stability of the system or the power transmitting system or element or the tooth is high as compared to cycloidal profile. Both are used according to the application. Now see the whole depth, the actual working depth. This is very important. Then addendum and dedendum. So this center, this circle known as a pitch circle, generally known as pitch circle, PCD, pitch circle diameter. So the distance of top flank from the PCD is known as addendum, and the bottom one known as a root. From the root it is dedendum. That is thickness of the tooth, width of space that will be accommodated by the driver or driven. If it is driver, then the driven tooth in between, this is the space. This is known as face. The bottom one is known as a flank. This bottom land, top land, and this is the addendum circle which we have. The most important thing is face width, because while designing any gear, face width plays a vital role in deciding the strength of the gear tip. Hence, the most critical part in the design depends on the face width of the gear. Circular pitch, see the circular pitch, distance between two consecutive. From here to here, this is the pitch, circular pitch. The rest is clearance circle and all. That is again important, but the main aspects are which I have explained right now. Into which the face width is again very important. The next is circular pitch, very important. Then the addendum and dedendum. Now, minimum number of teeth on pinion to avoid interference. Now, these are the generally advised number of teeth for pinion to avoid interference. Now, when I say interference, what do you mean by meshing of gears first? Now, please see and try to understand the fact that when we say gear tooths are meshing, so while we say gear tooths are meshing, it means that the profile which is used here, say this is the profile which is being used here. Now this profile, I'll explain later on, this profile. So the next tooth will come, here only and in this fashion, So we can say that this interference should be minimum. This interference should be minimum. So I'll explain with the help of fingers. Now please concentrate with the help of fingers. Say this is the driver and driven tooths. These are meshing with each other. Now, when I say these are meshing with each other, if the pitch circle, this is very important aspect in the design. Okay, so please mind it well. When I say the driver and driven, so if this is a driver, I'll say this is PCD of 1, then over here PCD of 2. A common tangent should be passed between these two. So this is PCD of 1 and this is PCD of 2. PCD of 1 and PCD. A common tangent, a common tangent will be drawn. A common tangent will be drawn at the point of contact. At the point of contact. So this is PCD1 and PCD2. Now, for the smooth transmission of power between the gears, gear tooths, say I'll take these two fingers itself so as to explain. Now, if this is the basic position wherein two PCDs are exactly meshing, then in that case, if PCDs are some distance apart, then tooth will be in this fashion and it will try to plug, it will try to hit this surface while rotating, and it will have a plugging effect on the internal face of the tooth. And if, say for example, these PCT gets inserted in each other, then the gear tooths will get locked itself. Interlocking will be there and there will be interference. To avoid this interference, the profile and the pressure angle, we must say the pressure angle or the gear for the gear tooth system is adopted as 14.5 full depth, 20-degree full depth, 20-degree stubbing and composite system. Now, we must have studied this in kinematics of machines, wherein what do you mean by full depth and stubbing. So it's a mode of gear tooth system wherein at different angles, 14.5 and 20-degree full depth, 20-degree, we have minimum number of required tooth on the pinion so that interference can be avoided. Now, again, the second important aspect is when this tooth gets meshed with each other, it will have a bending effect on this tooth. Say driver will have impact on the driven tooth, and if the strength of the tooth is not up to the mark, in that case the tooth may bend and will create interference with the other tooth, and the gear may get torn off or may get jammed or locked. To avoid that, we must calculate the strength of that beam or strength of that gear tooth by considering it as beam. So Mr. Wilford Lewis has considered gear tooth as a cantilever beam and subjected to bending moment due to tangential force acting on it as shown in figure. So this is the equation wherein we can calculate the beam strength of gear tooth. The next one, modes of gear failure. See, these are the modes of gear failure. I was discussing that scoring will be there, wear will be, pitting will be there, then plastic flow, then tooth fracture, fatigue, overload breakage. So these are the different modes of failure for the gear tooth. If the PCDs are not in contact with each other and a common tangent should pass through the interface, that's it. If it is following, then no problem. Otherwise, all these gear failures may occur. Wear will be there. Wear will be there. No problem. Scroaching will be there. Yes, will be there. And that's why in gear drives are generally oil cooled. Gear drives are generally immersed in oil bath so that heat can be dissipated. Because metal to metal contact, metal to metal friction will be there. And to dissipate that heat, we use gear oils. Yes, we use gear oils. Now, the fatigue strength. My dear friends, this is the general consideration in the design, wherein the maximum strength that material can withstand for a specific number of stress reversal, 10 to the power 6 to 10 to the power 7. This should be read as 10 to the power 6 to 10 to the power 7. 10 to the power 6 to 10 to the power 7 cycles. The material, if it is survived, then that is known as fatigue strength. The next one. So this is all about the fatigue strength. A simple question on the consideration of gear that which of the following can be used for power transmission. So intersecting shaft. If the axes of the shafts are intersecting, then bevel gears are used. Which of the following are true for worm gear? Worm is in shape of threaded screw. Thread on the worm have small lead. Worm imposes high thrust load and characterized by low speed reduction ratio. So all the three A, B, C are true, but less or low speed reduction is false, because worm and worm gear, the speed reduction ratio is highest one, and of the order of 1:36, 1:40, 1:60, sometimes 1:80 used in our automobiles. So this worm and worm gear, again, a very, very, very important aspect. So in the design of gear, I have discussed the very basic consideration of how the gear tooth may fail and how the strength equation will help us in designing the better gear design. So I hope you have got the idea as to how the design of gears will be done based on these conditions. Based on these conditions, say we have the next one is design of rolling and sliding contact bearings. Again, the bearings are the circular mechanical element. Bearings are the circular mechanical element. Although not always it is circular, any surface which supports the element known as bearing surface. But here, when I say bearings, mechanical bearings will have to serve these three basic conditions. Will satisfy with very basic. Number one, it will guide the motion. Number two, it will support the load. And number three, it will reduce the friction. That's it. Number one, it will guide the motion. It will, number two, very, very important, it will takes up the load acting on the shaft. And number three, that is very again important, it will reduce the friction. So bearings are the machine element that permit a relative motion between two components, the transmission of load from one to other with minimum friction. Now, how do we classify bearing? Bearings are classified depending upon the direction of load as a radial bearing and thrust bearing. So this is self-explanatory. Wherein we can say that radial bearings, the load applied on the shaft. Now, please concentrate. If this is the shaft, if this is the bearing, in this case, if the load is applied on the shaft is in this direction, say for understanding Y, and if it is in this direction, sake of understanding Z, then these two directions are considered as one known as a radial. So this is radial. If the direction of the applied force is in this direction along the axis, known as thrust or axial. So these are